The first part of my talk is concerned with the surface alignment pattern in the way you like. And so they talked about symmetry, chirality, and partially my talk is also related to symmetry control. Surface alignment is very, very general in liquid crystals, and this is what you see in the pneumatic phase when you inject liquid crystals in a liquid crystal cell that doesn't have aligning surfaces. And as soon as the surface has its own signature or symmetry, open symmetry, you tend to see the very clear sign of surface-induced alignment. So naturally, the effect of surfaces have been known from the very early stage of liquid crystal research. Officially, it is said that first liquid crystal was discovered in 1888, and soon after that, scientists like Lemon recognized the effect of surfaces. And they talked about moment effect, 1911, and rubbing actually discovered in 1920. And so combining a rubbing process with moment effect, then you get twisted pneumatic cell. So the really strong basis of the field effect LCD existed several decades, even before that became a practical LCD. And interest continues on and on, and I don't spend too much time explaining each of these topics, but what I'd like to mention is the number of interesting things increased almost exponentially as time passes. And then core thing is also surface sensitive. Many liquid crystals, including pneumatic, smectics, collectrics, all are very sensitive to surface conditions. So patterning came around somewhere around 2000. And this is one of the earliest examples we made. This is a kind of hexagonal or 6-fold symmetrical pattern on the surface by means of atomic force microscope. Even though the given title here is limited to photo alignment, my subject matter is much broader. Particularly the part 1 is concerned with the general description, how patterning can broaden the perspective of a surface effect. So this is just a video showing how transition takes place. Shrill texture emerges, and as soon as you have a lining layer, instead of just having this fairly random shrill texture, you end up with uniform so-called monocrystal liquid crystal, which is usable in twisted pneumatic display like this. And so applying electric field twisted liquid crystal, which is achiral, but twist is induced by the action of two constrained surfaces that undergoes a transition from twisted state to a vertical state that changes the propagation of polarized light. So when we talk about surface alignment, there are two critical parameters that we need to stick with. One is anchoring energy, which is the stability coefficient of alignment on the surface. The other one is the amplitude angle. We're primarily concerned with pneumatic liquid crystal, so we only have a director here, and the angle the director makes with the surface is called a predicted angle. And so from an engineering point of view, what they're trying to achieve is, first of all, the predicted angle as desired for the particular format of the display, and anchoring energy is something needed to stabilize that predicted angle. So all the methods so far developed are created to address the particular need of the display industry, or display design. But the bottom line of surface alignment is actually the control of symmetry, rather than the control of energy. Without the control of symmetry, it doesn't make sense to try hard to do any business of controlling energy. So all the time, control of symmetry is the most important thing you need to consider. A photon alignment does this particular thing in the way the photon action on the photosensitive material. Rubbing does this by buffing the surface with roller. So this is just a quick view of what I'm going to talk about. I'll come back to this later with more clear explanations. And I'm going to talk about patterning like this. Instead of just creating a uniform surface as has been used in liquid crystal displays, patterning means creating small patches of domains on the surface so that the alignment of liquid crystal is controlled in whatever way you want. This particular checkerboard pattern create two metastable states, state 1 and state 2. And by applying the electric field, you can make a switching between one state to the other and back. And there is a transient state. The symmetry here is a switching of chirality. And although this is it's better to like.
Slides here?
Yeah.
So, let's talk about autonomous system.
Yeah.
So maybe we need some like
Well, anyway, let me continue. So this is a surface state, so two-dimensional. But if you only have a uniform state, we don't have any chirality or any symmetry, just breaking of the left and right symmetry breaking. But as soon as we have a patterns arranged in this way or other ways, there is a possibility of having a completely different set of symmetry characteristics. In addition to the four-fold symmetry, which is the natural symmetry of this checkerboard pattern, you also, when this is combined with liquid crystal, it generates left-handed and right-handed chiral symmetry. Yeah, the switching.
So just a quick question, sorry for interrupting, to everybody. Is it better with light or without?
Without.
Yeah, yeah.
Don't move.
So at this moment, I just want to tell you that surface chirality is very, very important in relation to what they have talked about. So rubbing machine, the current generation 10 rubbing machine is so huge, and so companies are so secret that I couldn't have access to the state-of-the-art machine, so I only showed a very outdated machine. So even in the liquid crystal display industry, multi-domain alignment is a fairly common thing. And their objective of using multi-domain is to enhance the visibility or viewing angle characteristics. Liquid crystal displays were notorious to give incredibly poor viewing angle characteristics because of the optical uniaxial anisotropy. So depending on the angle you're looking at the display, the visibility can be good, can be extremely bad, or it can be completely reversed. So in order to overcome that problem, one solution is to split the single pixel into several different domains, having different orientations. So these are the things. The main difference with what I showed you in the previous slide and this one is the size. Normal pixel is 100 micron, 200 micron in size. So this single pixel is also 100 micron or so. The previous one I was talking about, this size is 1 micron or even smaller. And even with that small size, the symmetry characteristic can manifest itself very clearly. There are many techniques to make a pattern. Surface alignment, photo alignment, which is the subject matter of this talk, is currently most popular way to process the surface in a non-contact manner. Rubbing process is a contact processing, which creates a lot of problems, but photo alignment is just irradiating the surface with a particular polarization and then generate the surface alignment. And there are several others. Even older technique is oblique evaporation of, for example, silicon monoxide, and you can evaporate many different materials from an oblique orientation to get the alignment. And beam irradiation from oblique angle can also generate orientational constraint. So like I said before, what is really important is the symmetry breaking and how to break the symmetry that glass substrate or whatever substrate inherently has. And oblique processing breaks the symmetry in one way or another, and that's why all these processes can generate a uniform alignment. So symmetry breaking is the core. And so photo alignment, because we have used photo alignment fairly extensively to get pattern alignment, I'd like to give you just a general background what photo alignments are. And these are the typical materials being used for photo alignment processes. There are 3 different categories. Even if we irradiate the surface with fairly short wavelengths light, such as ultraviolet light, the internal chemical processes are different between one material to the other. One is for the cross-linking type, such as cinnamate molecules can undergo a cross-linking by means of excitation by UV light. And cinnamate historically has been developed as a photoresist for photolithography, and so there are really many cinnamate related materials that can be used for cross-linking photo alignment materials. Another important class of materials is azobenzene derivatives. They're small molecule azo compounds or oligomers and polymers that contain azo unit. And the important photochemical process that azobenzene undergoes is the isomerization from this straight, elongated form to bend form. This straight form is more compatible with liquid crystal, and it has a tendency to align liquid crystals along this direction. This is fairly compatible with liquid crystals, and it has a tendency, it doesn't really have any tendency to align liquid crystals in a preferential orientation. The last one, which is fairly different, is photo decomposition type. So the photo decomposition type, just UV light breaks the particular bonding along that particular polarization. So the in-plane anisotropy has been introduced by means of that angle-dependent photoassociation. So that requires a fairly short wavelength, ultraviolet light, and this works for near ultraviolet, and this works also in the fairly long wavelength. So one particular type, there are two, from a photoalignment behaviors, there are two types. One is a class of materials that tend to align liquid crystals perpendicular to the polarization direction of the UV light. So UV light is polarized this way, the final alignment is perpendicular to the polarization direction. And in this case, because you immediately see that there is no right-left-handed symmetry breaking. Left and right direction is completely symmetrical, so you don't have any predicted angle. So the liquid crystal is perfectly parallel to the surface, and which is perpendicular to the initial orientation. So in order to achieve necessary predicted angle, you have to take two-stage processes. One is the initial irradiation from the normal direction of linearly polarized UV light that dictates the direction of orientation this way. Up to this point, there is no predicted angle because of the symmetry. And by applying a oblique orientation, then that can break the symmetry between left and right. So in this type of materials, that historically this was the first type of material that was developed for photoalignment. So because of this problem of two-step processes, fairly new development was a parallel type of photoalignment materials. These aligning liquid crystals along the direction of polarized light. So in this case, you can immediately induce predicted angle by irradiating the surface from oblique angle. So even without knowing any detailed photochemical processes, or even without knowing anything about the chemistry, you can tell what this UV light irradiation does by looking at the symmetry of the system. And these are just animation to show you what the UV light does. And a fairly interesting development is that the symmetry breaking concept can be extended further. Instead of just aligning uniform the light by inserting a slit like this, by sliding the surface through these interference fringes, then you get a predicted angle, even for parallel or perpendicular type photoalignment materials. This idea also came from the symmetry breaking. How to break the symmetry? The symmetry breaking is coming from the relative action of light and the substrate. It is the way the substrate is being split under this texture light dictates which way the liquid crystal should be pre-tilted. So this is similar to rubbing process, classical rubbing process. That's why the name of rubbing came from. Okay, and this again is what's happening. So interestingly, this single shot normal irradiation process gives the liquid crystal a predicted angle. And at this moment, we really don't know what's happening inside of the photoalignment materials in terms of the cross-linking and the way predicted angle is generated. But it seems that the stability and efficiency of predicted generation is much higher than the uniform irradiation. And so this is the knowledge we have. Now this is just a prototype of a photoaligned surfaces done by JSR. JSR is the top company of photoalignment materials today. And all these processes are being done with a photoalignment irradiation system like this. This is a tabletop system as big as like this. And this can process a substrate size of 100 millimeter or 100 millimeter in a couple of minutes. So basically, this is very similar to mask aligner that is useful for photolithography process. So anywhere you have a mask aligner, you can do this photoalignment process. So by means of those photoalignment, this multi-domain display has been created and demonstrated to work in the way that it's supposed to. So this is the original twisted pneumatic viewing angle characteristic, which is very, very poor, and that can be improved dramatically to give us nearly isotropic viewing angle characteristics. So after all these introductory part, I'd like to mention a little bit about the physics behind what I've been talking about. So as a preparation, I need to explain a little bit about the elasticity of liquid crystals in relation to anchoring effect. So elasticity is, perhaps you already know that Gaussian-Frank elasticity can very precisely describe the elastic behavior of liquid crystal alignment. So when the liquid crystal is in contact with whatever restrictive surfaces in terms of morphology, in terms of alignment patterns, then what you get is the distribution of directors that minimizes the total free energy. And anchoring energy is, as I mentioned before, is the restriction, stability coefficient that tends to restrict the alignment in the way the surface alignment dictates. And so that is described by a characteristic length known as extrapolation length. K is the Frank elastic energy, W is the anchoring energy, and that gives rise to the extrapolation length. And so we can split into two regions. When the structure is larger than this extrapolation length, we can just ignore the anchoring, and we can assume the anchoring is strong, perfectly strong. In that case, elasticity can give us a perfect description of the behavior, and the Frank elasticity is the only ingredient we need to know. So because this is a liquid crystal follows the shapes, we call this soft liquid crystal regime. When the characteristic length scale of the surface is smaller than the extrapolation length, liquid crystal behaves as a rigid matter when it comes to the orientation imposed at the surface. So in this very short scale regime, we call this hard liquid crystal regime. So Frank elasticity is the basis of description of pattern surface. And what do you think is the key characteristic of Frank elasticity? If I was asked, I would say it's scalable, meaning that theory itself doesn't have any characteristic length scale. The real meaning is that R is the position vector. If you scale the position vector by a factor of lambda, if NR is the equilibrium distribution of the vector on any aligning surface, and scale function n lambda r is also a solution. So the whole thing is just scalable. You can just shrink or enlarge the system or distribution of the directors just by a factor of lambda. And following that scaling process, the free energy density is transformed with a factor of 1 over lambda squared. But the F itself doesn't change. That's why scalable behavior comes from. So the real Frank elastic free energy reads something like this. This is a well-known bulk component taking care of splay, twist, and then deformations. Each of the coefficient respective elastic constant. And it must be supplied with surface contributions. There are two surface contributions. One is saddle splay, the other one is splay band, K24 and K13. And some authors have used different notations, but basically they're same terms. And I like, because K24 term, saddle splay, plays a really important role. I need to explain what it is. This is a surface contribution. Okay, this is divergence of the vector. So when you take the volume integral, that divergence term can be converted to the surface integral. So the quantity inside this bracket is vector, which is quadratic to n. So even though this normally comes from the expansion of free energy in terms of the gradient of the vector, we can take a little bit different approach to explain what they are. And when we confine our attention to the surface contribution, what are the most general vector containing gradient of director, having the symmetry required for n versus minus n equivalent. Now these are two vectors. One is n divergence n, and the other one is a bend deformation like n cross nabla cross n, or which is exactly the same as n dot nabla n. So these are two most general vectors that we can construct using n and gradient of n. So these surface contribution is actually made up of these two terms. So from the phenomenological point of view, we can just construct a surface contribution by means of phenomenological coefficients A and B, containing this first vector, the second vector. This is a splay, this is bend. And we can rearrange the term in such a way that we have the first term looks like a subtle splay, and the other one looks like splay bend. So comparing with the original seen front, we immediately see that B equal 1/2 K2 2 plus K2 4, and so on. So in the geometrical meaning of these terms is the following. So we're working with this. This comes from the subtle splay, and it is more convenient to move on using a different notation for the bend term. And we take a local Cartesian coordinate, x, y is parallel, z is normal to the surface. And then we can write down this expression. And what we get finally is the expression like this. And these terms just cancel each other between these two. So what is really important here is to note gradient in the direction normal to the surface disappears, cancel each other. And we are left with the only lateral gradient. So saddle splay involves only lateral gradient. So these are the lateral gradient, and we can further transform the equation in such a way that we can simplify to involve only the gradient of z direction, the component of director. From this, we immediately see that these two terms just disappear when you integrate over the surface. This is complete derivative. So we are left with the last two terms, and if nz, the z component of the director, is just constant, with these two terms also disappears. So we don't have any surface contribution. And if we have a situation like this, these are all, so nz equal constant, we don't have any contribution. If the x component is a function of z component alone, and y is also a single component nz, then we can have a nz, capital Nz equals 0, so we don't have any surface contribution again. So these are simplest cases that we can think of. Both of them don't give any surface contributions. So what are the situations that we can have a real surface contributions. So using a polar coordinate, theta and phi, the theta is the polar angle with respect to z-axis, and phi is the azimuthal angle with respect to x. Then we expand in terms of a small sinusoidal deviation from that uniform orientation. Then we get first expansion. This is the lowest possible expansion of the contribution. That starts with the quadratic turn in terms of the amplitude of the variation. And this is what that expression dictates. And as you see here, we should know the component must be changing, varying. At the same time, azimuthal angle should also change, synchronize it in quadrature, or just 90-degree phase difference with respect to the z component. So this is what we need to get in terms of the one-dimensional change. And so this contributes to the total free energy. In this case, the free energy contribution may be positive or negative depending on the sign of the K24. So if the K24 is big, K24 can destabilize uniform orientation of the liquid crystal, inducing a spontaneous orientation distribution. So that particular one-dimensional orientation is exactly what's happening in blue phase. It is well known that blue phase consists of double helix, a double twist helical structure as shown here, and the stabilizing component is K24, and as I mentioned, if you carefully look at the how the double twist structure makes up the orientation on the plane surface locally, then you can immediately confirm that this is consistent with the non-zero cellular splay contributions. And the remaining thing is splay band elastic constant. And we can manipulate a little bit in a more symmetrical manner. And what is unique is, this is the cellular splay, this is the splay band. And with this manipulation, we can immediately see that this gives rise to a contribution that is only dependent on the normal derivative of NP. So all the lateral derivative is put into the cellular splay. And this normal derivative makes the minimization problem unsolvable. This is because this is surface only integral, and you can assign whatever value you want. So there is no lower bound for total free energy as long as K13 is non-zero. So this is a big problem, but microscopic conservation shows that K13 equals 0, so you can just ignore K13. So having said that, we can now discuss what surface balance can do. And so I'm almost running out of time for the first part, but just quickly, I finished the surface balance in the hard regime. This is so simple that we simply assume uniform orientation of the whatever surface constraint the pattern gives. And this gives rise to, this is required by the simplest form of anchoring energy. So what we need to do is to sum up the anchoring energy for uniform liquid crystalline contact with the surface. So N is just uniform, M is space dependent. And we can just manipulate and calculate everything. And so just an example, let us think about the undulated surfaces like this, which is common in group theory. Okay, for the first part of my talk, this is the last slide I'm going to use. And so this is just a particular example of how that hard regime can be used. And the height of this triangular cone, this is not triangle, square cone is capital H, the base is 2B. And we can calculate the total free energy by simply assuming the uniform liquid crystal alignment. And what happens here is the energy is dependent on capital H and B. And if H is too high, if the orientation is parallel to the surface, then we get homeotropic alignment, which is liquid crystal is oriented perpendicular to the surface. And when the height is sufficiently small, of course we expect the orientation is parallel to the surface. And going back to the previous calculation, okay, this is a specific condition that in this case you can have a London planar, and if the height is this big, you can get homeotropic alignment. And by extending this calculation to a general shape, you can just simply calculate how the orientation is affected by locally uniform isotropic planar orientation when the surface is modified. And so I stop here for the first part, and let me continue. That's it.
We'll take questions now or after the second part. So
there-
you have some good questions? Okay, see you back for